Hey guys, it's Mrs. Brayband. Just going over the target sheet for our graphing that we've been doing. If you remember, review 1 target and review 2 target. We have already done those. Those were from the last worksheet. If you want to look at those again, you can. You can obviously see the answers here. Just really fast. Remember, this is a difference of two squares. So 1 plus 1 minus set equals to 0. And you get each answer is positive and negative 11. Some of you are still working on how to factor these, but you're getting much better. So you can see how I did 2x plus 1, x minus 3, set equal to 0. Solve for x by moving the 1 with subtraction, dividing by 2, so you get negative 1/2. On the other one, solve by moving x minus 3 equals 0 by adding 3, and you get 3. So I think you get the idea. This one remembers a GCF, so don't forget your 0. And you've been really good at exclusions where, remember, you just look at the denominator, solve each one, set equal to 0, just like we did before. Exclusions, remember, are parts of the denominator that turn things into 0, and we don't want that, and that's what's going to lead us into our next lesson. So what we've got in target 3, as you can see, is 3 different rational equations that will give us functions that have those nice curves and branches. Also, they'll have usually, which makes them rational, those asymptotes. Sometimes they'll be 2, sometimes they'll be shifted, sometimes they'll be right on the axes. We'll have to look at the pieces of the puzzle in the denominator to tell us where those dotted lines are. So I'm going to do each part here, and at the very back of the worksheet I will show the graph for all of them. So here you've got vertical asymptotes we're looking for, and RDs, which we also call holes in the graph. So RD stands for removable discontinuity. I'll put that up here. Removable discontinuity. What that means is it's a point that you reduced and removed from the equation, so therefore you remove it from the graph because it breaks the graph up and makes it not continuous, so it shows a hole. So on the first one, you're going to look at the denominator, set that equal to 0. That will be your exclusion of x equals 2, and then on your graph, or excuse me, negative 2. And then on your graph, you're going to go right down the negative 2 axis, make either a dotted line or a squiggle to show that there's a break in the graph. Since nothing was canceled out in the top and the bottom, there's no hole. In the second one, you look at the denominators, x minus 3 and x minus 1. So just like the exclusions up above, you're going to set each one equal to 0. Remember, you really don't want that to happen. So your vertical asymptotes, which we call VACES for short, are at 3 and 1. So you're going to look at your axes here, like normal. You're going to go to 1, you're going to go to 3. You're going to put either a dotted line or a squiggle there. And those are going to be your vertical asymptotes. You want to look to see if anything was reduced. It was not. So again, there's no hole, no RD. On the third one, again, look at the denominators because we're looking for VACES. So it's things you don't want to happen. So you set them equal to 0 and you solve both. If you look over here, I've only done 1. So I only did 1. So I only used the one that's remaining. So if you noticed, there were 2 parts of the puzzle that were identical. So we canceled those out. When you cancel them out, they now become a different discussion, and that's the discussion of where the hole is. So the one that you cancel is the hole. Again, if you remove it, it becomes a hole. The one that's left behind turns into your vertical asymptote. You're going to solve each one of them, but the hole's a little different. So let me finish the VACE first. X minus 1 equals 0. That's going to be x equals 1. That means you go to the 1 on the x-axis, draw a squiggled line for an asymptote, or a dotted line, and that means you can't cross it and break it. For the hole, it's a little different. You get x equals 2, just like the setting it equal to 0, but you've got to decide what your whole point is that you're going to use an open circle on. So you put that 2 that you found into the equation that you got up here after you reduced. So if you put 2 right in there, you're going to get 1 divided by 2 minus 1, which is 1 divided by 1. So that y value now is going to go into the point. So you got 2 from canceling, 1 from plugging in, and that's going to become a hole on your graph. Let me scooch this up a little bit. Excuse the wiggles. And now I can talk you through the next target, which is x-intercepts and y-intercepts. They are similar. If you notice, I'm using the same exact equations. So the VASI, remember, is in the bottom, but the x-intercepts now, you want to look in the numerator. So you look at the numerator, you look at the numerator, you look at the numerator. Oh, geez, it goes away. That'll be a different discussion. And you try to decide what is the x-intercept. So you take the x-intercept, you set it equal to 0, and that will be your answer for your intercept. So you go right to the graph and put a dot on 0, 0. That's a point you want to graph. Here it's x plus 1 equals 0. You solve it, that means negative 1 comma 0 will be the point right on the graph. But look over here. When you reduced out, you turned this numerator into 1. So if you're trying to figure out what your x-intercept is, there's no x value to set equal to 0, so you don't have the variable. That means there's not an intercept. So there's not going to be a dot on your x-axis. All right, that's x-intercepts. Y-intercepts are on your other axis, and they're a little trickier to find, but not too difficult. You're going to go back up to the original equation, and everywhere there's an x, you're going to plug in 0. Plug it in, substitute. Now you're going to work it out. 0 in the numerator, 2 in the denominator. That's going to be reduced to 0. So your y-intercept now is 0, comma 0. In other words, you plugged 0 in as a substitution. You got 0 out when you worked it out. So for the second equation, nothing cancels. So I'm going to go 0, 0 everywhere. 0 in for x, 0 in for x, 0 in for x. And then I work it out. So 0 plus 1 is 1. 0 minus 3 is negative 3. 0 minus 1 is negative 1. Multiply the denominator. You're going to get 1 divided by 3 positive. That is now the dot on the y-axis. The last one here for your y-intercept, excuse the messiness, sorry. Again, you're going to plug 0 in, but remember when you looked, you got this new beautiful reduced equation that's smaller and simpler, so you're going to put 0 only in there. You can do it up here if you want. It's just going to get a little messier, so I like the smaller one. Again, put 0 in right there. 1 divided by 0 minus 1. 0 minus 1 is negative 1. 1 divided by negative 1 is negative 1. So you're going to put a dot, a point, right on the y-axis. Now I'm going to flip over and do the other pieces of the puzzle, and then by the time we're done, we're going to graph it. So looking at the top, let me scooch in a little bit. Hello. There we go. Okay. Now, this is called a horizontal asymptote. So it's like the vertical asymptote, so it's a dotted line. I use squiggles because it's easier to see, but it is dotted because you are not really seeing it. It's a guiding line. Here's the tricky thing about horizontal asymptotes. Sometimes they get crossed. Verticals never get crossed, but sometimes horizontals do. So especially when our equations get super complicated, that might happen. So don't panic. But I'm going to show you how to find them. There's a couple different rules that I'm going to show you. There is a third rule that comes up in our further math classes. It's not going to come up here, but I'm just going to show you the first two. So what you want to do now, it's a little different steps than all the other page. For the horizontal asymptote, you want to figure out where does my graph level off horizontally. So as I go far left and far right, what does my graph do? How far does it go out left and right? So what you do is you take a look at your lead in both the numerator and the denominator, what's in front, and you look at the powers of both of them. So let me rewrite this again. You look at the first ones and you look at what the powers are. If the powers are identical, like this first equation, meaning they're equal, all you do is you go in front and look at their coefficients, one here and one here, and you divide them out, 1 divided by 1. That's going to turn into 1, and now that horizontal line that you used to have on the axis now gets shifted up and it moves through 1 now. So now your curve's going to gravitate towards it instead of the x-axis. So again, if the powers are equal, you look at the numbers in front and then you divide. So this rule says I'm going to put y equals a over b, and those a's and b's are the coefficients, meaning the numbers in front of your lead terms in your numerator and denominator. Okay? Now, look at this one. This gets a little complicated. If you look at this, right now that's power 1, but if you did your distributive property here, do you notice you'd get that from the top? I'm only looking at the leads. And first times first is x squared, that in the bottom. Yes, there's more in the bottom. Yes, there's more in the top, but we're only looking at those guys. Do you see this power is a 1? This power is a 2, so they're different, and they're specifically different. The numerator power is smaller than the denominator. That means the numerator is always going to be tiny, and the denominator is going to get really big really fast. So when you have a tiny number divided by a big number, that's always going to get really super close to 0. So that means your horizontal asymptote is the x-axis. And that's a very typical problem. So if you look at the bottom, these are the exact same equations that we've been working on the whole sheet. But now we've got everything listed, and we're going to graph it all. So let's just review. The VASI, bottom, -2. The HASI, compare your powers like above. They're equal. 1 divided by 1 is 1. There it is. Your x-intercepts come from the top, so there's your 0. You put a dot. That means the y-intercept in this case is exactly the same, because when we plug in 0, we got 0 again. Now I did try another point here just to kind of predict where I was up here, but you could just, once you realize your dots are here, then what you could do is kind of just hug the asymptote magnetically. Don't touch it. Hug this asymptote because you're going through that 0, 0, and then realize, you know what, I need to do the same thing across here, kind of like the parent function. So I'm going to recognize there's just a little bit of space from here to here, so a little bit of space from here to here, and I'm going to graph it. Now, the estimation is not perfection. You could do what I did up here and plug in a 1, see what happens. Plug in a -3, see what happens, and you'll get the same picture. I'm going to go all the way to the third one because it's a little easier to graph, and then I'll do the middle one last, okay? So the third one, remember, was that cool one that crossed off the x minus 2's and had a RD, which we call a hole. It gives us a prettier, smaller equation. And so what you're going to do here is notice again, the bottom gives you the VASI. There goes at 1. The HASI, because your powers, look at your powers. That power is less than that power. That power is a 0. That power is a 1. That's less than that. So that's going to go right on your y-axis. Your x-intercept is not involved because there's no letter. Your y-intercept, once you plug in zeros, is going to be -1. So there's that dot right there. And then watch the graph. If you've got this dot here, curve, 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 hit the dot, curve, 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 curve. You get close to your asymptotes, but not exactly. Copycat that on the other side. Voila, you are done. I'll do the third one in another video.